Mic test, mic test. I think everything is working. Mic is working. Um, what's up, everybody? Happy Monday, happy Monday. Um, hope everyone had a great weekend. I know I did. Um, it was just a great relaxing weekend for me, and I hope that the weekend was good for everybody else. Um, I missed streaming. I missed, this, and so uh, I'm glad that we're streaming today. Picking back up on networking essentials. Today we're going to start chapter 6 and we're going to learn some really important things. Um, so let's get right into it. Let's not delay any further. Let's get right into it. So actually, just what did we talk about? Last chapter, chapter 5, we talked about the rules, right? There are three elements in communications, right? You need a sender, a receiver, and then you need the medium. Like how did the data travel? We talked about protocols being rules. Uh, we talked about why rules matter. We talked about uh, all these devices, right? In today's age of technology, with hundreds of millions of devices on the internet, who's regulating these things? Who's making sure that everybody is following the same standards, the same protocols and rules? We talked about the organizations. Um, we talked about um, we talked about obviously the TCP/IP and the OSI model, and I can't emphasize enough how important it is to truly have a firm grasp and understanding of the TCP/IP and the OSI model. It is very, very important to uh, know those models, like know it by heart. Um, you really got to know it by heart. And then we talked about the rise of Ethernet and how we've gotten to the Ethernet cable that we all know today. We talked about how in the beginning, early stages, there were many companies with their own proprietary cables, but we talked about how that led into a lot of complications, and so all these companies came to an agreement. Let's just use this one standard cable. And yeah, so today, chapter 6, we're going to talk about encapsulation. We briefly talked about encapsulation last chapter, um, and we mentioned that encapsulation, you're taking data and you're putting it in another message, and then taking that message and putting it in another message, right? When we go down the OSI model, um, let me just pull it up. Uh, Let me just pull it up. So when you encapsulate, okay, yeah. So when you encapsulate data, right? When you encapsulate, meaning you're sending data, uh, it starts from the top down. Starts top down, and at layer 7, 6, and 5, the data, the packet, the it's going to be known as data. And then when it gets to layer 4 transport, we talked about TCP and UDP. Depending on which protocol you use, it can either be known as a segment or a datagram. And once, and so you take the data and then you capsulate it in transport. And then now the data is now a segment or a datagram. And then you encapsulate transport into network. And we talked about uh, once the segment encapsulated turns into a packet at layer 3, and then you take the packet and then you encapsulate it again to layer 2, and then at layer 2 the packet is now known as a frame, and you take the frame and then you put it and then you take it to the physical mediums that we talked about, such as Ethernet, right? And Ethernet just takes that data, the binary data, and then it sends it over to the receiver. And if that's in encapsulation, the receiver does something called decapsulation. So the process of placing one message, and then we'll use the analogy that they use. They use the letter. We'll talk about that and get into that. But um, the process of placing one message into another message is called encapsulation. Decapsulation occurs when the process is reversed by the recipient and the letter is removed from the envelope. So the analogy they used was a letter and a envelope. So just to go back, so we talked about how encapsulation, you start from the top down. De-encapsulation, when the receiver gets the message, it's going top up, right? So the receiver starts de-encapsulating here at the physical level, and then it opens up the frame, right? The frame we talked about, layer 2, this is your MAC addresses and your NICs. So the frame is then de-encapsulated into a packet, and we talked about at layer 3, we talked about IP addresses, IPv4, IPv4, IPv6, right? And so you take the packet and de-encapsulate it again at transport, which then turns into either, depending again, the protocol, if it was a TCP protocol, it's a segment, and if it was a UDP, it's a datagram. And then de-encapsulate once more, and then in the upper levels, upper layers, this is where it's known as data. So they used a letter, and we'll play this video. So here's the letter, and then they're going to encapsulate this leather. They're going to encapsulate the letter into the envelope. Um, and there's going to be a lot of information, right, that's in these headers that we're going to talk about soon. In this specific chapter, we're going to be talking about Ethernet frames, and we're going to talk about the fields in the frame. Um, but yeah, you see, I don't think we can skip that, and then let's get right. So this is an IPv6. Um, this is the packet for the IPv6. We'll get into this a little later in the course. Let's talk about Ethernet frames, right? So we talked about at layer 2, the data, the packet, it's called a frame in layer 2, and the frame can be either a minimum of 64 bytes and up to 1,518 bytes. They do not count the preamble and the SFD. Um, and the SFD, if I is the frame delimiter. Um, what does the S stand for? I'm sorry. Let me pull up SFD. That is definitely not. That is not what I wanted to look. That is wow. Um, what is SF? I'm It's part of the preamble. I'm just want to think of what is SFD, some frame delimiter, start frame delimiter, start frame delimiter. Sorry guys. But the preamble and the start frame delimiter, or SFD, these 8 bytes are not included in the 64 to uh, 1518 bytes, 1518 bytes. These 8 bytes are not included in these, right? In this 64 to 1518 bytes. So there's a minimum and a maximum. Anything smaller than a 64 bytes, anything smaller than that is usually known as a grunt frame. Um, and anything larger than this is known as a jumbo. And if you're wondering, well, what happens if it's less or more? It's automatically dropped. So that when the receiver sees it and it sees that it's abnormal, it just automatically drops it. But so we have the preamble and the start frame delimiter. Um, and then let's see. There's the destination MAC address. That's the uh, obviously that's where this frame wants to go to. There's the source MAC address, the the sender, right? The receiver and the sender. Each of these are 6 bytes, and we talked about how 1 byte equals 8 bits. 8 bits. 8 bits. Right? So 48 bits, 48 bits. The type and length, this is going to indicate the protocol that's used in layer 3, either IPv4 or IPv6. And then the data, what kind of data are you sending? And then the FCS, this is the frame check sequence. This is just making sure that everything is okay. It's basically just checking and making sure everything is okay, nothing corrupted. Um, and the SFD, so if you're wondering what the preamble and SFD is, the preamble and SFD, that's just the beginning of the frame. Um, letting the other we'll get more into the preamble and SFD, but really just you need to know that this is just the beginning of the Ethernet frame, and then um, the most important parts is to know the destination MAC address, the source MAC address. Um, just know FCS stands for frame check sequence. Just general knowledge of knowing that Ethernet frame fields, the usual size can be anywhere from 64 to 1518 bytes. That's generally what you want to know. All right, so let's check our understanding. The process of prepending protocol information with information from another protocol is called, I believe it's going to be in caps. Framing, I don't think we even talked about framing, or packetizing. And encoding, that's not even going to be the answer. When an Ethernet frame is sent out and interface, the destination MAC address indicates um, when the Ethernet frame is sent out and interface, the destination MAC address indicates the MAC address of the device which is on this network that will receive the Ethernet frame. That seems like the answer. The MAC address of the NIC card of a device which is on this network or another network that will receive the Ethernet frame. That also sounds right. Um, the MAC address of the NIC card that sent the Ethernet frame, that is not the destination, that would be the source. The MAC address of the router, well, we'll get into that, but when the when it when the sender knows that the packet is not in its network, it automatically sends it to the default gateway. We'll get into that a little bit later in this chapter. Um, I think it's gonna be this one. But then again, the NIC card of a device. Let's go with this one. We'll go with B. I think B is a little bit more specific with the answer. So we're gonna roll the dice with B. A could be also right. Which Ethernet frame field indicates the beginning of the Ethernet frame? That's the preamble and the start frame delimiter. The Ethernet protocol is what layer of the OSI model? That's going to be layer 2. Let's check. Okay, so this one was wrong. So I think it was wrong because see the reason why I thought this wasn't going to be right was because another network, and that goes along with the address. This another network. uh, We're gonna get it into that later in this chapter. If anything is outside of its network, the MAC address will automatically be the default gateway, the interface that's facing that network on the default gateway. But let's check again. Yeah. So yeah, we'll go into this and see why that was wrong. So let's move on. So we talked about physical and logical addresses. We talked about how physical addresses are MAC addresses, right? When you think of physical, remember when we talked about physical topology, we thought of um, like where are the actual devices located? So and think of physical as in literally the NIC card, right? The NIC that's literally integrated into the device physically. Um, and when you think of physical, think of MAC addresses, and when you think of logical addresses, think of IP addresses. Think of IP addresses. And in IP addresses, there are two parts in the IP address. There's the network portion of the IP address, and then there's going to be the host portion. So it mentions that all hosts connected in the same network are going to have the same network portion of the IP address. It would make sense, right? If all of these computers right here, all these hosts are located in the 192.168.200 network, if they're all connected, I mean, if all of these hosts are in the same network, it would make sense that they all have the same logical network portion. Um, and then this part right here, the 1, 2, 3, 4, and just in this scenario, um, these are the hosts. This is the unique identifier, right? Not all hosts, right? You can't have four hosts with the same host portion. That just doesn't work, right? So these four hosts are on the 192.168.200 network. And then we see that these four hosts are going to be in the 192.168.1 network. So two completely different networks, right? And so if this host wants to communicate to, let's say H3 wants to communicate to H6, it needs to talk to the default gateway, the router, and the router will then forward the message to H6. And remember when I mentioned that when when a computer knows that it needs to send data outside of its network, the MAC address automatically is going to be assigned. The destination MAC address for the packet is going to be by default the default gateway, the interface that's pointing this, right? So this interface right here, this the cable right here. Let me zoom in. The cable right here, right? The port, the Ethernet, the interface right here that's pointed towards the 192.168.200 network. If H3 wants to send a packet outside of this network, the MAC address, the destination MAC address is by default going to be set for the interface of the default gateway that's pointing towards the 200 network. And and that's just by default. Hierarchical analogy. Mm, let's. I think watching the video. Let's see. Um, okay, so there's something called a hierarchical design, right? And there are three layers to this design. There's the access layer, there's the distribution layer, and there's the core layer. The access layer, this is where generally you're going to see your local hosts um, and your switches. And then the distribution layer, this is your route. This is where you're going to, the routers, this is where routing is going to take place. And then the core layer, this is where you have your high-speed routers. That's just providing crazy internet speed. So yeah, access layer, think of your switches. You're going to think of your layer 2 devices. Switches provide the connection to the distribution layer device, usually a layer 3 device. So yeah, so access layer, think of your switches. There are layer 3 switches, but in this for learning purposes, we're just gonna say switches for access layer, and and when you're in the access layer and you're talking to hosts within the same network, right? If this computer wants to talk to this computer, it does not need to go to the distribution layer and have the router route towards to an outside local network, right? To a remote local network or you the, if it's in the same network, there's no need because the switch can just forward it towards one of the other hosts that are within the network. But if this host right here wants to talk to this host over here, it needs to access the distribution layer, and then the router will then know, okay, what's the best path for me to get this host's message to this host. And that's where, again, distribution layer, this is, think of your routers, um, and then there's your core layer. And this is where the core, I mean, this is like, think of, I mean, you probably haven't seen, this is a crazy router here, um, but these kind of routers are providing, I mean, if you think about it, there are hundreds and hundreds of devices in a corporate setting. You're going to need very powerful routers to push out massive amount of of of, internet speed, right? You need massive amount of bandwidth to push out data as fast as possible, right? We talked about bandwidth and throughput and so again, in a corporate setting, when you have hundreds of devices on the same network and they're all trying to access the internet, you're going to need powerful routers to be able to push out that kind of push out that kind of data, right? So yeah, think of the core layer as the backbone of the network. So let's check our understanding. An IP address is considered a logical. An Ethernet MAC address is considered a physical, which address does not change when a device is connected to a new network. I guess I did skip over this, but it's always going to be logical. We talked about um, how if it's the physical address, if the MAC, so if again, if the host knows the message is intended for a host outside the network, the destination MAC address by default is going to be sent towards the MAC address of the Ethernet of the interface of the default gateway that's facing that router, and then we haven't got into it yet, but um, it there is something called ARP. There's something called ARP, and we'll get into it a little bit later. But basically, the router will then send the pack. And then, so once the packet or the frame or packet or data gets to the router, the MAC address. So once the router receives the MAC address, the or not MAC address. Once the router receives the packet, the MAC address then will be changed because the router received it and it sees, okay, this packet is meant for this host outside the network, so let me re-encapsulate this and put in new information. I think I may have com- the way I just described that may have been a little bit confusing. I'm sorry. I promise you, uh, once we get past this, I'll be able to explain it a little bit better. Which portion of an IP address uniquely identifies the device on the network? That's the host. Remember, host portion is unique. It identifies, right? Which design layer provides connectivity to devices on Ethernet? Remember, Ethernet. That's going to be our uh, that's going to be our access layer. Jeez. Yeah, I just brain farted. I was like second guessing myself for a second. Let's check. Oh no. Which address does not change when a device is connected to a new network? Let me see why. What? The physical address does not change when the device is connected to a new network. Okay, I guess I read the question wrong. Oh man, I read the question wrong. Whoops. I'm so sorry, guys. I completely read that question wrong. So yeah, oh my goodness. So it doesn't matter, right? I can move my computer. Oh my goodness. Like I just totally misread that question. So I can take my laptop, right? I take my laptop and I'm at home. Sure, my logical address can change, right? My logical host address can change every single day, actually, technically speaking, every single day. Um, like if I go to, for example, right, at my home, I have a certain logical address. When I go to a coffee shop, my logical IP address may not be the same because that coffee shop may have a uh different network address. Like for example, my home, again, maybe my home is the 192 by default set to 192.168.1. And maybe when I go to the coffee shop, uh, their network is 192.168.2. So automatically my logical address has changed, right? And then I go to the library and the library network is 192.168.200. Again, my logical address has changed. But no matter where you go, your MAC address, the NIC, right? The network interface card that's physically integrated into your device, no matter what, doesn't matter where you go, right? You can go to the library, you can go to the coffee shop, you can go to your home, you can go to your friend's house, you can go to corporate. That physical address will never change, right? Doesn't matter if I'm in North America and then I go to Canada and then Halifax, my MAC address is always going to stay the same. So I guess this was part where I skipped, and I do apologize. I read that question wrong. For some reason, I assumed that it was talking about something else, but yes, when a device is connected to a new network, like I said, if I go to a coffee shop, a library, my friend's home, if the network address is different, then automatically my IP address, my logical address is going to change because of that. But my physical address, the MAC, the NIC that's physically in my computer, laptop, that will never change. So access layer. Um, so let's start with the hubs. So there was something called a hub, and this is exactly why we got away with hubs. Okay. So hubs are they're super old, right? No, I don't think anybody really uses hubs anymore, and there's a reason why. Because hubs are stupid. Because as you just saw, if this host wants to send um, to H7, the hub is going to flood everything. And what do I mean by flood? That like right there, right? So think about it this way. Not only is that problematic because everybody's receiving it, um, what if H1 wanted to send something to H7? What if H1 wanted to send something to H7, but at the same time H8 wanted to send something to H3, and then H4 wanted to send something to H5, and then it kept going like that, right? Well, unfortunately, they have to take turns. They literally have to take turns. Like H1 sends to H7, and then once that's completed, then H8 can then send its message, and then it floods again. And then let's say H8 wants to talk to H3, and once H3 gets it, then H4's turn to send it. Like it takes turns, right? So it's super slow. Um, and the fact that it has to flood everybody like that, and then people have to take turns waiting to send messages. Um, only one message can be sent through an Ethernet hub at a time. Um, so you can see how problematic that was. It was very slow, and sometimes, um, it was possible that two hosts sent a message at the same time. This is what we would call a collision. This is known as a collision. So imagine if H8 and H1 they both sent a message and the hub was flooding, um, those messages would just start colliding each other. And this is what we call a collision, and the message is unreadable by hosts, and then it has to be retransmitted again. So we have moved away from hubs. Hubs is really just outdated technology. I don't think anybody uses hubs. We've now moved to switches. And switches are smart. Switches can multitask. Switches don't have to take turns waiting for each host to send. No, it can multitask and send multiple messages at the same time. And this is why we've moved away from hubs. And um, and yeah, I mean the switches are just much more smarter, and they can work with multiple devices. And again, it doesn't have to wait for a host to send like a hub. It can just multitask. And this is why switches are better than hubs. And we moved on from hubs. So for this demonstration, let's see. So you saw that, right? H the switch did not have to flood. And this is also reason why switches are smarter than hubs, because the switch has something called a MAC table. And the MAC table is basically a switch, right? So switch when basically switches record all of this information, right? So that let's say for example H1 wants to send to H7. Let's say H1 wants to send to H7. It's going the switch, the way it knows that is that it already filled all these MAC addresses in its internal MAC table. And you're probably wondering, well, Mo, how did the switch learn all of these MAC addresses. And some of you may be thinking, well, maybe it's because it's connected via Ethernet, and that's a pretty good idea. But there's something I mentioned it before. There's something called ARPing that we will get into a little bit later in this chapter. But this is also another reason why we moved on from hubs, because hubs, they're not smart. They don't have MAC addresses, or they don't have MAC tables. It doesn't have the capability to store that information and for next time, the next time, right? Like if H1 wants to send to H7 through a hub, the hub literally has to flood every single time. It doesn't know H7's MAC address. Like it doesn't. It's just literally gonna flood and then and then just gonna be like, okay, which one of y'all is it? Doesn't matter the fact that H1 literally sent a message to H7 literally 2 seconds ago. The hub is that stupid. It just doesn't know. Versus switches have MAC tables and it records it so that for next time, um, it just knows, right? It doesn't have to flood or anything like that. Um, Not to say that switches don't flood, because switches do flood. They will flood, but we'll get into that a little later. But this is also a reason why switches are just smarter. Not only are they able to like send multiple messages at the same time, um, they also have a MAC table. And I just do want to clarify that the MAC tables like are not stored permanently. They're just temporarily stored into RAM memory. Um, and the MAC table is like filled like I think like it gets filled like every 15 minutes or something like that. So after every 15 minutes, um, it just automatically like again sends out ARPs and then refills its MAC table. So the MAC table is not permanent. It's a temporary table stored into RAM, and like every 15 minutes, it just refreshes the MAC table. Um, and I think that's pretty much all you need to know. The MAC address table, I just literally talked about it. Let's watch this. So I think it's yeah, here we go. So that's what we talked about. So I mentioned earlier, Mo, how does a switch know? Well, how does a switch know where to send the packet if it doesn't, um, let's say like for example, we put in a new computer in the network and we connected it to the switch. Well, how would H3, how's H3 going to send a message to to that new host? And that's a great question. And we just saw in this video, the switch is going to flood. And it's going to flood. And everybody that does not, um, and everyone who does not have that destination MAC address, they're just going to drop it. But whoever has the destination MAC address, they're going to respond by saying, that's me, that's my address. And it's going to send it to the switch, and it's going to fill in the MAC address, and then sends it back to the source. So yeah, again, this is what we would call a flood, and then the switch immediately learns its MAC addresses. So again, notice as well, did you notice as well that the Ethernet port 3 also got its MAC address filled in? So um, this is again, everyone that did not have that specific destination MAC address, it did not respond. Did not respond. Only the one that had the 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 destination MAC address, the one that had that matched up with it, responded. But notice how this empty entry was also filled in. This is why, again, switches are smarter than hubs. We don't like hubs. Hubs are stupid. They can't do these things. So let's check our understanding. Ethernet switches make their forwarding decision based on what field of the Ethernet frame, and this is going to be the destination, right? They're forwarding based on the destination. Ethernet switches add entries to their MAC address table based on what field of the Ethernet frame, destination. When a switch receives an Ethernet frame and the destination MAC address of the frame is not in its MAC address table, the switch will forward the frame out of all ports except the incoming port, drop the frame, add the source MAC address to the table, add the destination. So when a switch receives an Ethernet frame and the destination MAC address of the frame is not in its MAC address table, it's going to forward them all out, right? Remember that video we just saw? It's going to flood, and whoever has the destination MAC address is going to respond. But let's say there were other entries that weren't filled in, it's going to fill it in there as well. Ethernet hubs are considered obsolete. Cutting edge? Nah, they're not cutting edge. They're stupid. I think we should be good. Let's check. Okay, we got something wrong. Ethernet switches add entries to their MAC address tables based on what field of the Ethernet frame? Is it source? Let me see. Okay, let's see why. Um, Add entries to their MAC address table based on the spelled source as doors. That's interesting. I mean, I can understand source, but let's see. What happens when the new host is, yeah, the destination MAC address is not in the table? Um, yeah, see, this is what I assumed is that if it's not in the table, it's going to just flood and fill out its table that way. Um, Ethernet switches add entries to their MAC address table. Hmm, interesting. I'm not going to argue and say Cisco's wrong on that. But okay, source MAC. Broadcast. So, I even explain what a broadcast is, let's just watch this video. So, basically, a broadcast message is, um, so again, in this example, host 1 is new to the network. And so, for it to let everyone know, hey, I'm here, it's going to send out a broadcast message. And this broadcast message, it's the MAC address is going to be FFFF, FFFF, FFFF. And each F in the hexadecimal notation represents 4 ones in the binary address. If I'm correct, um, what is it? 10, A is 11, um, B is 12, C is 13, E is 14. Wait, I'm so sorry. Wait, A is 10, B is 11, C is 12, D is 13, E is 14, and then F is 15. F is 15 bits in the hexadecimal. So if a host wants to get in contact with everybody, it sends out a broadcast message, and the broadcast message is again in FFF, FFF, FFF. Um, and again, for this example, this host is new. And so it wants to let everybody know, hey, I'm new and I'm in here, I'm in this network, just want to say hi. And then we saw that it literally just broadcasted out and everybody got it. And then not only did everyone receive that information, these switches can add that entry into its MAC address table. Okay. Okay, and here it says on a local Ethernet network, NICs only accept the frame if the destination address is either the broadcast MAC address or else corresponds to the MAC address of the NIC. So again, what this is saying is if the MAC address doesn't match up to its MAC address, like let's say it receives a message and the destination MAC address does not match its MAC address, it's not going to accept it. It's just going to drop it unless it's a broadcast message. Broadcast message, all devices are going to accept that message. Um, let's say, for example, well, what if I have the logical address? I know the IP address of the device, but I don't know its MAC address. And I kept saying it before. This is where something called a protocol called ARP, Address Resolution Protocol. This is where it comes into play. So so this computer knows the IP address of this computer, but it doesn't know the MAC address. And again, when you send messages out, you always need the logical IP address and you need the MAC address. So what can we do? Well, there's something called ARP. And let's just play the video. So ARP, so the computer is going to send out an ARP request, and then the switch is going to flood it out, and whoever has that, hey, and so in this example, this device is like, hey, that's me, that's my address, it's going to reply, that's me. And so the host, therefore, now is like, okay, now I have the MAC address, I can send the packet over. Again, you're always going to need the IP address and you always need the MAC address. You need those two. If you want to establish communication, you're always going to need the MAC address and you're always going to need the IP address, depending on the protocol, right? But if you want to establish for communication, if you want to communicate, you're going to need both the IP and the MAC address. And again, if the host only knows the IP address, it's going to send out an ARP, right? And the ARP request, ARP is layer 2, but it has the IP address, right? So it's going to have that layer 3 information, right? So layer 3, and then you encapsulate it, and then the ARP is sent out, and then the switch gets that, and the switch is like, okay, let me flood this out. And then he's going to be like, hey, that matches my IP address. Let me respond. And that's my IP address. And so I'm going to respond saying, hey, that's me. Here's my MAC address. Send it back, and the switch is going to forward it back to H1. And then H1 can therefore now send the whatever message that it wanted to send. The destination, let's check our understanding. The destination MAC address of the Ethernet broadcast is, again, FFF, FFF, FFF. When an Ethernet switch receives a frame that is broadcast, it will forward the frame out all ports except the incoming port. Probably the answer. Forward frame out all ports, including the incoming port. Well, why would it need to include the source? It wouldn't make too much sense. Switches are smarter than that, right? Forwards the frame only out ports that need the broadcast. Nope. And then drop the frame. Nope. So I think A is going to be the best answer. Host A has an Ethernet frame to send to host B on the same network. Host A knows the IP address to host B, but not its MAC address. What message will host A send to determine the MAC address of host B? And this is going to be a ARP request, right? It's going to be an ARP request. And then the receiver that matches that IP address is going to reply, hey, that's me. Here's my MAC address information. An ARP request is sent out as a broadcast, so all devices on the same network will receive it. That sounds like a pretty good answer. A broadcast, so all devices on the network and other networks will receive it. Remember, ARP is layer 2. It's not going to, and it's only going to work on internal networks, right? It's not going to leave and go to a different network. So probably not it. And we know that unicast, it's not a unicast. So most likely A. Host B receives the ARP request. Host B will return an ARP reply if the IP address in the ARP request matches its own IP address. Probably the answer. The MAC address in the ARP request matches its own MAC address. Well, this is wrong, right? Because clearly we're sending an ARP, we're sending out an ARP because we don't know the MAC address. We just know the IP address. So this is not the answer. And then again, the IP and MAC, that's not the answer. So most likely A. Host A sends an ARP request and receives an ARP reply from host B. What is in the ARP reply that host A did not know? And that's going to be host B's MAC address. Let's check our answers. And we're 5 for 5. All right. And I think that's going to conclude this chapter. Man, we went quite a bit. 53, what are we at? 53 minutes so far. So yeah, that's it. It's a lot of information. I know that um, I definitely could have explained it a little bit better, and that's on me. And obviously, I'm trying to be better, right? And again, the purpose of me doing these is to like, one, it's a good refresher for me, but number two is just like I want to make sure that I know these things, and to really know these things, you need to be. I think if you to really know if you know these things, you should be able to teach it. So um, that's why I'm doing these streams. Um, but I'm trying to get better myself. So next time for sure, when we do move on to chapter 7, and this is gonna be about routing, layer 3. Um, I'll definitely try to be a little bit more prepared and try to have like better examples. Um, but yeah, what did we learn today? We learned encapsulation, right? Taking data and putting it into another piece of data and then putting it into another piece of data. And then we learned the opposite, de-encapsulation. Um, we just briefly talked about de-encapsulation, but for the most part, we did talk about both encapsulation and decapsulation. And we also talked about the Ethernet frame, right? Remember our layer 2 frame, layer 3 packet, layer 4 segment or datagram, and then upper layers known as data. So we learned about the Ethernet frame. We learned that we learned the SFD and preamble, the start frame delimiter. We realized that that's not included in the frame field. That's 64 to 1500 bytes. We learned that there's a destination and a source MAC address. We learned that there's a type field. We learned that there's the data portion, and then we learned the check frame sequence that's at the end to make sure everything was okay. We learned the hierarchical network design, the three layers, the access layer, think of your switches, your hubs and switches. Distribution layer, think of your routers when you're trying to communicate outside of the networks. And then we talked about core layer, the backbone. This is how hundreds of devices are going to be able to perform at high speed because you have these powerful routers, these machines that are being able to provide large amount of bandwidth, which therefore allows lots of throughput. Speeds are increased. Again, we talked about the access layer. We talked about hubs and switches. We talked the differences between hubs and switches. Hubs are stupid, and we know why they're stupid because all they can do is flood, and they have to take one. Messages have to be sent one at a time versus switches can multitask, right? They don't have to wait one at a time. They can just send messages, and we learned that it doesn't need to flood. Why it doesn't have to need to flood? Because it has a MAC table, and we talked about how the MAC tables are filled. We talked about broadcast messages, right? And we talked about, most importantly, we talked about ARPing, address resolution protocol. Um, that's all I have for today's stream. Again, next stream, we're going to be talking about routing layer 3, and I will do my best to do a better job of that one. But thank you guys so much. I hope you guys have a great night, and I love you guys, and till next time, peace.